Okay, so one of the reasons in logistic regression, as I mentioned in the perceptron, and one of the difficulty is this activation function is not differentiable. So, and what we can do is we can replace this, this activation function by a sigmoid activation functions. So, so previously an activation function is a step function. So that means this is equal to 1 if z is bigger than 0, it is 0 otherwise. But turns out this is a really bad choices of the functions. And what we can do is we can replace this activation functions by a sigmoid activation functions. So so this function is defined as follows: is sigma of z is 1 over 1 plus exponential of minus z right here. It's the value of this function is between 0 and 1. So you can think about the function actually looks like this. So this is asymptotically goes to 1 right here. But this is, so at point of 0, the value is evaluated at 1/2. Okay, so as a comparison, my step function is just being like something like this. So, and you can think about this is like, it's like, and relax this, step function to be, something that is infinitely differentiable. One of the property of this sigma mod function is sigma of minus z right here. It's equal to 1 over 1 plus square root of z. If we multiply, and if we multiply exponential minus z on both hand side, this can be written as 1 minus a sigmoid of z. So this is some important properties that we need to use. And of course, this actually gives you some value between 0 and 1. It is not and perfectly give me the class 1 and 0. So that's why we actually build, and you need to build the models directly to indicate under what kind of situation it will be predict as class 0, under what kind of situation it will be predict as 1. So the model is given as follows. Is if you are given an x, so this like logistic model, sigma of x w right here, it can be interpreted as probability that x belongs to class 1. So this is very important. So, and what does that mean? Mathematically speaking, is probability that y equal to 1 conditional on x and the w is basically it's sigma of x w. So this is actually it means give you, so we build a model that the probability that give to as y equal to 1, it is sigma xw. So this is just being our our assumption here. So as the result, the probability y equal to 0, it's nothing but 1 minus sigma xw. Okay. So this is, I mean, just build a model. So and this is model part, and the second part is we need and you need to make this prediction. So the prediction is this probability. I mean, if you're given this probability, the x is in the class of 1, if probability is bigger than half. So that means it's and the probability to be 1 is bigger than half, so it's more likely to be 1. If the probability to be 1 is less than half, so that means it's more likely to be 0. So and it will be predicted as 0. Okay, so this is basically what happened here. So, and from graph, we can tell this everything here that, and I mean, so if x dot w is bigger than 0, so this is being classified as 1. And if x dot w is, I mean, less than 0, this will be classified as 0. So this part is very similar to the perceptron, but the difference is my sigma right here, it's actually infinitely differentiable rather than the phi that we had before. So this actually is also a linear classifier. So so this is also a linear classifier. So and you can see right here, it's because we are just taking the product between x and w, which is just simply being the same idea that we have. But the difference is we change this and activation functions. So the beauty of everything is we have some probabilistic interpolations of our models. If we have some probabilistic estimations of our models, we can using like likelihood, we can using estimators, we can using all these and statistical tools that can help us to either justify or even and further navigate other possibilities. So the first thing that we can think about is we can find the likelihood. Right, so the likelihood is to say this probability that you observe of yi, I1 from 1 to n, conditional on x of I. So this is my feature, and given some parameter. We know all these data, I mean, throughout these courses, all training data are sampled in the IID manner. So that means we can actually make this a multiplications of each individual data. So this is multiplication of I from 1 to the n of P of yi. So this is just because we using the properties of independencies, x of I and the w right here. So and of course, in general, we don't work with the log and the likelihood like directly. If we have a whole data, we usually work with the negative log likelihood. So it's NLL. So NLL of W is basically negative logarithm of likelihood, right? So this becomes minus summation of I from 1 to the n of the logarithm of P of X of I. Right, so this is, it's work like, in terms of, general ways. And what is this? This is given as follows. Right, so it is 1, that would be sigma xw. If it is 0, that would be 1 minus sigma xw. And obviously that's very, very complicated. So can we make it simpler? So in fact, we can write everything into more compact form. The more compact form is as follows. And we can verify it momentarily. So this is actually equal to sigma of X of I W power of yi and multiply the 1 minus sigma of X of I 1 minus yi. So we can try that out if what is that? If yi is equal to 1, right? So this becomes sigma, and this becomes 1, this becomes 0. So this becomes sigma of xi w. If yi is 0, so that means this is 0, this is 1, this is 1 minus of sigma of x1 I w. All right. So, and you can see this is a much more compact form right here. And if we're using this compact form right here, so I'm going to move this back. This is equal to minus of summation I from 1 to the n. So we can move the power down once we take the logarithm. So this becomes y I of the logarithm of sigma x of I w. Let's just put the plus. Plus 1 minus yi and multiply the logarithm of 1 minus sigma x of I like this. So this is nothing but just put down, power is down and take the logarithm of each component. Okay. So this is quite straightforward. But in fact, this has some interesting meanings here. So this corresponding to something called, and this is like negative log likelihood of my logistic regressions if we're using the sigmoid and activation functions. So I want to argue this whole thing is equivalent as use cross entropy loss. So what does that mean? And what is the definition for the cross entropy loss? If you have two Bernoulli distributions, one is P and the 1 minus P, another is Q Q 1 minus Q. So the cross entropy is defined as HPQ as being minus P. So this is a vector here. P block Q minus 1 minus P block 1 minus Q. Okay, so basically this actually measures kind of like distance between two probability distributions. For fixed, P right here, HPQ is minimized at Q equal to P. Why? And we can see that we can take partial derivative with respect to Q. This is equal to minus P over Q minus 1 minus P of 1 minus Q times minus 1 here. So this becomes minus P over Q plus 1 minus P over 1 minus Q. We can combine these terms, minus P, 1 minus Q, plus Q, 1 minus P. So the cross term cancels out. This becomes Q minus P of Q, 1 minus Q. If we set this to be 0, this goes to P has equal to Q. So that means when P equal to Q, that will be reach some local stationary point. But we can show later, I'm not going to show it here, is we take the partial derivative, second order partial derivative with respect to Q, it's always bigger than 0. So that indicates P equal to Q is actually reaches the minimums. Right, so this is very important. And also, if we're using this whole idea and we can match right here. So this is your P, this is your and this is will be your Q. So this is actually you can think about as we are calculating the cross entropy of P equal to Q, the P, and let's define this P Pi and Qi, where Pi is equal to Yi and 1 minus Yi, and Qi as a vector equal to sigma x of I and 1 minus sigma of x of I. Okay, so if we define these two, this term in this bracket is nothing but cross entropies of this Pi and Qi. Then this is becomes summation of, I believe is minus summation of I from 1 to the n of cross entropy of Pi and Qi. Okay, we sum them together at the end, and we're trying to minimize so with respect to W. So there is some and connections between negative log likelihood versus cross entropy loss in the setup of the logistic regressions. Okay, so next is we all know we need to find the gradient of this negative log likelihood. So this is extremely important. So let's find out one by one. So this is, we have this minus summation. Okay. And we have yi and a sigma here. So you have to be a bit careful. And we need some additional condition here to ensure we can get it right. So this right here, sigma prime of z, right? So we know this is, so this is 1 plus exponential minus z to the inverse. So if we take derivative, this will becomes minus 1 of 1 over 1 plus exponential of minus z square of minus exponential of minus z. So minus sign becomes plus sign. This is exponential of minus z divided by 1 plus exponential of minus z squared. Now you can write down everything separately. 1 minus 1 over exponential of minus z and exponential of minus z over 1 plus exponential of minus z. So this is equal to sigma of z multiply 1 minus of sigma of z. Okay, we need to use this particular fact right here. All right, so first thing first, it's yi here. So yi divided by logarithm of this. So this logarithm will be on the denominator, and the sigma of x of I and the w will be on the denominator. Then I'm going to take partial derivative with respect to this sigmoid function. So we know this becomes sigma of x of I w 1 minus sigma of xi of w. And then I need to take partial derivative with respect to x times an inner product of w. So this is becomes x of I transpose. Okay. So you can do very similar things for the bottom one. This is 1 minus yi divided by 1 minus sigma of x of I So we do similar things, but right here it's we take partial derivative with respect to 1 minus of sigma right here. So this will be minus sigma x of I w 1 minus right. I believe that's correct. Yeah. Then I'm going to multiply same thing xi transpose. Right, so same thing. Okay, so then we see these cancels out. And also these two cancels out. What remains? It's yi multiply 1 minus sigma of x of I transpose minus 1 minus yi sigma of x of I, this then x of I transpose. Okay, so I believe that's correct. So then what we do is we can factor out this xi of transpose. It's a common factor here. And we here is yi times 1, yi times a sigma. So this is minus. Minus minus cancels out with a positive. This is becomes yi subtract sigma of x of I and x of I transpose. Okay, so you can see right here, each individually, I'm going to move this minus sign inside. So this is, I mean, if we think about this is equal to 1 over summation I from 1 to the n of this Li of W, right? So I move this minus sign inside. This is becomes plus, this becomes minus. Each individual right here, it is gradient of the ith component of the loss, gradient of Li. Okay. So this is very important because if we can calculate this thing explicitly, it actually, and we can using the stochastic gradient descent in these cases. All right, so, and also, and you can further take second derivative, you can find out the hashing is positive definite. That implies this loss function is strongly convex. That means my negative log likelihood has a bowl shape. That means if we have a unique lowest point, always. So this is really ideal. So we can always find some and the lowest point somewhere. And of course, we could also and vectorize it, but for now that won't be necessary because we are going to summation I from 1 to n. We're not going to actually submit and sum them together. We're going to and perform that with a stochastic gradient descent. All right, so so that will be it for now. In the next lecture, we are going to actually talk about, I mean, a little bit deeper in the stochastic gradient descent and actually implement this type of and the logistic regression from scratch. That will be in the next lectures.